Shame, isn't it, Herb?
What's a shame, Don?
Well, all this ice and no party. Maybe it's because the nearest karaoke machine is thousands of miles from here.
Maybe it's because the nearest anything is thousands of miles from here.
Oh, yeah. Well, who needs a party when you got Beakman?
Fact. Spiders have transparent blood. I'm Beakman, and you've just broken into Beakman's world.
Where's the Beakmeister?
I don't know. He's late. Forgot his key again. Now, isn't that just like Beakman?
Candygram.
Nope, not Beakman.
Someone looking for me? Hey, what are we all standing around for? We've got discoveries to discover, inventions to invent, wonders to wonder about.
Now, here's a question with a real aquatic flavor to it.
Oh, good. Did Shamu write in for a sushi recipe?
Actually, Lester, killer whales would much rather dine on penguins.
Penguins?
Hear something?
No.
Janet Thomas of Austin, Texas asks, Dear Beakman, how come a boat made out of steel can float, but a nail sinks?
Ooh, provocative query, Jana. For something to float, it needs to be less dense than the stuff it's floating in.
Density. The mass per unit volume of a substance under specified or standard conditions of pressure and temperature.
What? Density. It's easy. Let me show you what the good professor means. I have a beaker of these marshmallows, which I've packed down, and a beaker of water. Even though they both take up the same amount of space, one of them weighs more than the other.
I get it. Whichever one weighs more is denser.
Precisely. Since we know that for something to float, it has to be less dense than the stuff it's floating in, it's a safe bet that if you put a marshmallow in a beaker of water, it'll float. Abso-floatin'-lutely. Now, let's try the same thing with nails. The beaker of nails and the beaker of water take up the same space, but this time, the nails are denser. So, a nail will sink.
Oh, well and good, Beakman, but you see, that letter did not ask you how come a marshmallow can float or a metal can sink. It asked you how come a boat made out of metal can float.
Lester, you have hit the nail right on the question. Now I'm going to show you that I'm not all wet. This tank is filled all the way to the top with water, and I'm going to get into it to show you the next exciting chapter of...
Why a Steel Boat Floats.
To understand that, you need to understand displacement. Here we go. Oh, yeah! Now, you see the water spilling out here? That's because I displaced it, or pushed it away.
Yeah, displacement. He's pushing it from this place to that place, and afterwards, guess which rat has to clean up this mess?
Now, here's the amazing part. If you were to take all the water that spilled out of the tank while I'm floating and weighed it, it would weigh exactly the same as I do. Uh-huh. See? Okay. You know about density, you know about displacement. Let's put them together. Let's pretend that this stuff here is a special kind of water that's not watery. If I take the ship out, I'm left with a hole in the water. Now, the ship that fills this hole in the water has to weigh the same as the water it takes to fill up this hole. If the ship weighs any more, it will sink. Bada bing, bada bang, bada boom. Here's something you can try at home. All you need is some aluminum foil and a sink or bowl full of water. This foil is made of metal, just like a ship. Oh, and by the way, do you know the difference between a boat and a ship? It's their size. A boat can fit on a ship, but a ship cannot fit on a boat. But a boat. Here's my boat. Nice, huh? And it floats. Now, take your foil boat and crush it into a ball. Now, you gotta make sure you get all of the air out. That's really important. All right, now this foil weighs exactly the same as it did when it was a boat. But in this new shape, it pushes away or displaces less water. In other words, it weighs more than the water it displaces. So, it sinks. And that, Janet Thomas of Austin, Texas, is why a boat made of steel can float. Thanks for asking.
Coming up next, potatoes. Oh, potatoes. The last straw. To all you couch potatoes, this bud's for you.
Beakman's World will be right back. Now back to Beakman's World.
It's time to nuke your noodle. Here he is, the boss of the brain trust, the Viscount of the variable, the Clarence Darrow, the straight and narrow, the one, the only, the Beakman.
You flip 'em, I'll rip 'em. Now let's whip 'em.
I just can't take this anymore!
Oh, here's one from Sabrina Wambolt of St. George, Utah. Dear Beakman, why does a woodpecker peck?
Answer: a woodpecker pecks to pick little insects called grubs out of the bark of trees or to chisel out a nest. It also uses its beak to send messages.
To whom? Oh, they're bookies.
No! They use their beaks to send messages to Beakman.
No, to their fellow woodpeckers. Next question.
Next question. Dear Beakman, what causes waves?
Bored sports fans?
I think they're talking about the waves in the ocean. What causes them?
Bored fish. I'm kidding. They are caused by wind as well as earthquakes and landslides on the ocean floor. Fast fact. Most people put on their left sock first.
Here's one for you. Do all male lions have manes?
No. As a matter of fact, some of them don't.
Question. Dear Beakman, what's the most common name in the world?
The most common name in the world is Muhammad.
Hello, Muhammad.
Hi, Mohammed.
And speaking of common, about 10 million people in the world have the same birthday as you.
Dear Beakman, does a penguin have a love life?
Ah, this is interesting. Male penguins actually romance a female by offering small pebbles. If the pebbles are accepted, he knows he's won her heart.
No wonder these flowers didn't work.
Yeah, Don, you should have gone with the pebbles.
You know what they get for a dozen pebbles?
Really rocked you, huh?
Fast fact. A cockroach spends more time cleaning itself than a cat does.
Dear Beakman, what
Wait. I hear distant thunder.
There's one wing nut short of an erect descent.
Why, it must be time for
The Beakman Challenge!
Style 118.
Any experiment should be performed at home only with adult supervision, and all appropriate safety precautions should be taken. All directions should be followed exactly, and no substitution should be used.
Lester, my good rat. What would you think if I were to tell you that I can stuff this straw through this uncooked potato?
I'd say sure.
Now, wait a minute. Wouldn't you say that's impossible, Beakman? You're off your nut, Beakman. You're one fry short of a happy meal, Beakman. Wouldn't you say all of that?
Well, yeah, but you see, I've been burned a few times on these challenges of yours, so if you say you can do it, you can do it.
But putting this flimsy straw through this rock-hard Idaho potato, isn't that impossible?
Go ahead. Dazzle me.
All right, here we go. There.
Wow. How'd he do that?
A straw is a cylinder, a tube, and cylinders are one of the strongest shapes we have. Think of a table with just one leg. It won't stay up very long, will it? Neither will a table with two legs. Here, check it out. Now, a table with 3 or more legs is a lot more stable. That's why most of our tables at home have at least 4 legs. The more legs we add to a table, the harder it is to tip over and the more weight it can hold up. Now, that's what I call a stable table. So if you think of a cylinder as a table with so many legs they all touch each other, you'll see why it's such a strong shape. Here, look at this. Hard to believe, but this piece of paper can hold up this brick if we roll the piece of paper into a cylinder and keep it together like that. And check this out. But don't try building a house like this because it's only strong from the top down. See, if you push it from the side...
Come here next. We'll go up, and away. Take off is in just a moment or so, so don't go out and away.
Beakman's World will be right back. Back to Beakman's World.
Hello, Josie. I was just studying the intricacies of the atom here.
Was it an atom with curly electrons or the kind with Shem electrons?
Actually, it was Mo electrons. Anyway, what you got there?
Came in this morning.
Oh.
It's a question from J. Anthony Brown of Atlanta, Georgia. Dear Beakman, how does an airplane stay up?
Why, it takes a nap during the day. Okay. That is an exquisitely uplifting question, J. Anthony. High five yourself for coming up with it. You know, it says here that the first flight by a plane that had controls and an engine was on December 17th, 1903. Orville Wright was the pilot, and he flew 120 feet. Let's see, that's about the distance of 3 school buses. Orville made the journey in 12 seconds at the speed of 30 miles per hour. He built the plane with his brother Wilbur, and the flight took place in Kitty Hawk, North Carolina. Interesting book. Wow, look at this. The airplane with the largest wingspan ever was the Spruce Goose. It only flew once on November 2nd, 1947, and the Spruce Goose was 319 feet, 11 inches from wing to wing. Holy cow, that's longer than a football field.
I'm sure it is, Beakman, but you still haven't answered the question. What makes an airplane fly?
That's easy. An airplane flies because it's got an engine. Gee, I also have to do all the figuring out around here.
Sorry, Lester, but that answer simply does not fly with me. You see, an airplane flies because of the shape of its wings.
It's just not the engine, because that's where it gets all of its energy.
Hey, see for yourself.
Now boarding.
This toy plane flies using the same principles as a real plane, except the rubber band here is the engine. Let's see if it'll fly without the wings.
Oh, pobre avión.
See, it moves fast, but no can fly. With wings, however...
Arriba!
Oh, did I say engine? I meant wings. A plane needs wings to fly.
In fact, airplanes without engines are called gliders, and pilots have kept them up in the air for as long as 24 hours using air currents as their energy source, their engines.
This is probably a really dumb question.
Well, the only dumb question is the one that isn't asked. So, what's your question?
Okay.
Come on.
How Does the wing make the plane stay up?
Why, that's a great question. It stays up because our old friend air pressure always tries to be equal.
You always say that, and I always get confused.
Well, it's really a question of balance.
Balance, huh? Hey!
What?
This looks like a job for Balance Man!
Yes, Balance Man, strange visitor from this planet whose sole mission is to remind us that people and nature must stay in balance. And he works for scale.
Nature seeks balance.
That's it?
You know, you always seem a little disappointed whenever I appear, young lady. Why is that?
Oh, no. I'm not disappointed with you, Balance Man. But I'm just disappointed that my good friend and mentor Beakman can't be around to see you ever.
Can you believe this?
Tell me, young lady, do you still have that toy airplane you had before?
Oh, yeah, sure. How did you know that?
Oh, why, I was sitting up in my den in Superhero Land watching you. Before, yes. All right, now, tell you what, forget the toy airplane, have your piece of paper. Thank you. Now, the air pressure is even all around the paper. But watch what happens when I change the balance by blowing. Ha ha! My blowing made the pressure on this side lower than the pressure on the other side. The paper was pushed towards the weaker, low-pressure area. When I stopped blowing, I became dizzy because I was hyperventilating. But also, the air pressure on both sides was balanced again, and the paper returned to its original spot.
So it lifted up because it created an imbalance.
Zaloom!
Zaloom! Hey, Beakman says that.
Oh, why, that's simply a coincidence. A bizarre coincidence, young lady. Ha ha. So you see, high pressure tends to push things into low pressure areas until they balance. They're always trying to be even, balanced, like me. And now, I'm out of here. I gotta go balance my checkbook.
Did I miss anything?
Balance Man was here!
Really? Balance Man was here and I missed him? Oh, man.
Oh, give me a break.
He explained about high and low air pressure, but I still don't understand how an airplane stays up.
Well, the answer, Josie, is blowing on the wings. The answer is blowing on the wings. A wing uses air pressure in a really neat way. Look at this cross-section. What do you notice about the top of it? Josie?
It's curved.
That's the secret. The fact that the wing is curved on the top and flat on the bottom affects air pressure.
How?
Let's go to the scope. Here's the airplane at rest. The air pressure on top of the wing is the same as the air pressure under the wing. But look, when it starts moving forward, something really interesting happens. Let's take a closer look. When the air hits the front of the wing, the leading edge, the air divides. Half of it goes on top of the wing, and half of it goes below. But since the top of the wing is curved, the air on top has to go faster to meet up with the air on the bottom. The faster air moves across a surface, like this wing, the less pressure it puts on that surface. The wing is caught between low air pressure on top and higher air pressure underneath. And you know what happens when something's caught between low air pressure and high air pressure.
Sure do. It gets pushed.
Right again. In the case of the airplane, it gets pushed up. It flies. Bada bing, bada boom.
Now that you know how planes stay up, find out what was the fastest plane that ever flew. Beakman will tell you when we come back.
Beakman's World will be right back. And now, back to Beakman's World.
The fastest plane ever is the SR-71, also known as the Blackbird. That thing can really haul. It was clocked at more than 2,193 miles per hour. You know that that's about 3 times the speed of sound?
A little sound barrier humor. And speaking of airplanes, it's time for us to return our seatbacks to their phone, upright, and locked positions.
Yeah, make sure your carry-on luggage is safely stored till we see you next time.
Don't forget those tray tables and happy landings from Beakman's World.
Herb, I think I'm going to go flying.
Penguins cannot fly, Don.
You know, they used to say the same thing about people.
Ooh, that's very good. You're learning a lot from Beakman.
Beakman can fly?
Well, he's on the air.